The beginning of a new era in astronomy. For the first time, scientists have detected ghostly particles that are not just extraterrestrial, but extragalactic. They come from millions of light years away, where stars explode or supermassive black holes swallow cosmic matter in tremendous vortices. Neutrinos. They're among the most abundant particles that exist, and the most mysterious. Every second, 100 billion of them race through our bodies at close to the speed of light, without our ever noticing. They move unhindered through the universe because they can fly easily through most matter.
For me, the neutrino is the closest thing to nothing we can imagine. It has zero size, zero charge, mass very close to zero, and it interacts so weakly with everything. But somehow or other, the neutrino isn't nothing. It might be the key to the universe.
For astrophysicists, the universe is one huge laboratory in which most things still have to be discovered. The matter of which the stars, planets, interstellar gas clouds, and humans are composed only accounts for a mere 5% of the universe's mass. The rest is an enormous, unsolved puzzle. The human eye is woefully inadequate to see everything in the universe. Astrophysicists are looking for apparatus that will help them investigate the tremendous events in the cosmos, for which they have any number of theories, but precious little concrete information.
They are not simply neutrinos, and in our case neutrinos with particularly high energy. They are neutrinos conveying a message. They are messengers. They tell us something about the object from which they come to us. This object must be something in which incredibly high energy is released, many times higher than in the Sun. We are looking, for instance, at neutrinos arising from dark matter annihilation processes. These may give us an indication of what dark matter is.
10 years ago, an international team of scientists started to build a gigantic detector to catch these high-energy neutrinos in one of the most remote places on Earth, the South Pole. Deep in the ice, the scientists are looking for flashes of light triggered when a neutrino collides with matter. With a mobile drilling station, the research team has melted countless holes, kilometers deep into the Antarctic ice cap. Here, the ice is so deep and pure that the detector, which measures a cubic kilometer, has sufficient space and ideal conditions. A hot water drill, which draws down its own weight as it melts the ice, has prepared the way for photosensors in the crystal clear ice. The upper layer of the ice sheet consists of snow. The snowflakes change as they are pressed down deeper and deeper over many thousands of years, from graceful ice crystals to compact, transparent ice. The meter-high flakes are transformed into firn, a layer of compacting ice. More and more snow presses the air out of the firn. It becomes denser and even more compact, until finally it is a body of ice almost free of air. The scientists have introduced photosensors the size of basketballs into the ice, on separate strings like threaded beads, up to a depth of 2.5 kilometers. Within a single day, the drill hole freezes closed. When the work's completed, a cubic kilometre of ice is full of sensors. The gigantic detector is now ready. Deep within the crystal clear ice, where it is pitch dark, thousands of highly sensitive photosensors wait for minimal but far-reaching traces of light. And these traces only occur when a neutrino collides with an atom in the ice. In 2013, scientists found the first conspicuous light signals in the ice cube detector.
We can't trap the neutrino itself. It interacts with matter very rarely. If we're very lucky, it collides with an atomic nucleus, releasing secondary particles, some of which move hundreds of meters to kilometers in straight trails through the matter. Behind them, they pull a cone of light, which is called Cherenkov radiation, after the man who discovered it. And this light is what we detect with the ice cube. We found high-energy neutrinos for the first time, Ernie and Bert. They had such high energy that it was extremely unlikely they were created in the Earth's atmosphere.
These neutrinos must have come from outside our solar system. When such a high-energy cosmic neutrino, which is much smaller than an atomic nucleus, collides with an atom in the ice, it creates a light signal that spreads over several hundred meters. The discoveries of Ernie and Bert were the breakthrough after decades of research. Scientists worldwide are searching for these messenger particles from the distant universe, also on the other side of the planet, in Europe. A research institute on the French coast of Toulon is a base for a tremendous Mediterranean project, the Cubic Kilometre Neutrino Telescope, or KM3-NET. Antares, a small prototype of the deep-sea neutrino detector, already sends data here.
Each box corresponds to one of the detection strings. Each cross represents the height and the time of the photon that was detected. 20 years ago, we started the development of the Antares telescope. It took some while to learn the tricks of the trade of how to build very large infrastructures, very deep in the sea. Antares was in fact 12 detection strings, but our project that we're building now, KM3-NET, will be many hundreds of strings. So this will dramatically increase the chances and essentially guarantee that we will be able to have unambiguous detection of cosmic neutrinos.
Neutrinos are all around us, but we have no idea where they come from. These elementary particles that have 1,000 times more energy than those from the world's largest particle accelerator, the Large Hadron Collider in Geneva.
The most trivial neutrino source is humans. All of us have potassium in our bodies. The small amount of a radioactive isotope of potassium, potassium-40, undergoes beta decay, which produces neutrinos. Our bodies emit between 4,000 and 5,000 neutrinos per second. But more important ones for us, physicists, are solar neutrinos, which we have already identified. In fact, on every square centimeter, say, on every thumbnail, 60 billion solar neutrinos arrive every second, and they fly through us, irrespective of where we're standing, facing away from the sun or towards it, or in a deep cave. Imagine 60 billion neutrinos.
The sun burns hydrogen in its core at a temperature of 15 million degrees Celsius. Light particles, and also neutrinos, are emitted. The sunlight we see has required thousands of years to pass through the sun's successive layers. Only the neutrinos leave the core immediately. Just 8 minutes after their creation, they reach the Earth. But these are low-energy neutrinos.
We're looking for neutrinos that come to us from entirely different processes, not from nuclear reactions, but from massive acceleration processes due to cosmic accelerators like the LHC accelerator in Geneva, but that accelerate many, many times faster with much higher energy. We're hoping that cosmic neutrinos will give us information we can't get from any other source.
Neutrinos are a small part of the cosmic rays that constantly rain down on the Earth's atmosphere. We've known about this high-energy particle radiation for more than 100 years. But where and how the particles originate is still a puzzle. All we know is that it consists largely of atomic nuclei, mainly protons. Here in the Mediterranean, the KM3 net detector will be built in 3 sections. One of them off the coast of Italy, another off the coast of France, and the third off the coast of Greece. They will be 4 kilometers underwater and digitally linked to form a giant detector. In its maximum extension, KM3 net will be 10 cubic kilometers large. Whereas ice is the detecting medium of ice cube at the South Pole, the detecting medium here will be liquid water. But deep-sea conditions make entirely different demands on the planning and construction of the detector. To read the data from the water, the scientists are installing an infrastructure on the seabed, which will gather the data, bundle it, and transfer it via special deep-sea cables to the analysis stations on the coast. With an instrument the engineers call WORM, which uses extreme water pressure, they dig a deep channel into the upper layers of shell and stones until they strike a harder layer of rock. On this solid foundation, an accompanying diver lays the cable and immediately covers it with shell limestone and mud for protection. Zeuthen, south of Berlin, is the location of one of the leading centers of neutrino research, the German electron synchrotron, DESY. This is where a team of particle physicists developed the sensors from which Ice Cube at the South Pole is constructed.
In this glass sphere, you see a photomultiplier tube. It is inside here, and it's very light sensitive. When a single photon strikes this side, it produces a tiny electrical current which can be read out by the electronic module that's located in the upper part of the sensor. Let me show you. This is the glass sphere that protects the sensor from the enormous pressure deep in the ice. And inside we have the electronic module, which amplifies and digitizes the tiny electrical current and then sends the digital signal up to the surface.
Thousands of synchronized sensors measure the precise time and strength of the light event and communicate the data. In their laboratory, the researchers are already working on the next generations of light sensors. They should be cheaper, simpler, and more efficient. One idea is to conduct the Cherenkov light through coated tubes. The scientists are looking for ultraviolet light. The postdoctoral student, Jakob van Santen, is getting ready for his first assignment at the South Pole.
You have to be really fit to fly to the South Pole. I have to get a thorough medical checkup. When I get the okay, I'll set off for Christchurch on New Zealand's South Island. I'll have to wait there for quite a while, until the weather conditions are just right. Then I'll fly 8 hours to the Antarctic coast, and then maybe after a couple of days take a flight of 2 hours to the South Pole. I've been working on the Ice Cube project for a long time, but I've never seen my experiment. I'm really looking forward to that. And going to such a special place, which only few people have been to so far.
The journey to the South Pole is an adventure for the young scientist. The Antarctic is larger than Europe. Its surface includes land, a continental ice sheet, and a gigantic ice shelf. 98% of the region is covered in snow and ice. In summer, the sea ice surrounding the southernmost continent melts to less than 3 million square kilometers, 1/6 of its winter surface. Because of the altitude of its terrain, the extremely low temperatures and low precipitation, the Antarctic is also one of the driest regions. In fact, the world's largest desert. It's summer here, and it's high season. Researchers come to the South Pole in summer. Only a skeleton crew remains during the dark, cold winter to keep the detector running. Everyone who comes here is excited to reach the South Pole, but some suffer from altitude sickness from the moment they arrive. It takes a few days to acclimatize. For the researchers, the new Amundsen Scott South Pole Station is an oasis in the middle of the ice desert. It guarantees their survival. The station can accommodate several hundred people. Everything here is simple and practical. But Scott and Amundsen, who were the first to reach the South Pole more than 100 years ago, would be astonished by the comfort and technology. This is an astrophysics hotspot. Deep in the eternal ice, the researchers are discovering cosmic light signals. IceCube is searching for neutrinos that have flown through the Earth, ones that entered the northern hemisphere. Ones that entered the southern hemisphere are looked for in the Mediterranean, for only neutrinos can fly through the Earth. The KM3 net detector will also search for particles that have traveled through the Earth. Since the Mediterranean is more than 5,000 meters deep, Catania, on the east coast of Sicily, is an ideal spot for a research station. A team of European scientists is here to install the first section of the detector on the seabed. Physicists have adapted the structure of the photosensors to deep-sea conditions. Water pressure, salt, and sea currents are formidable challenges. The sensitive electronic module has to be protected to make the most precise measurements at any moment.
The difficulty is that these objects have to be placed at a depth of 4,000 meters. Everything has to be correct, because it's extremely hard to pull them back up out of the water to repair them. So everything has to work perfectly before the mission begins in the sea.
The physicists register the sensors so as to be able to sort the data they will receive from the depths. In the Scott Amundsen station at the South Pole, Jakob van Zanten is now feeling at home. He can reach the ice cube on foot.
It's a beautiful day. Almost no wind. Summer temperatures of minus 30 degrees Celsius. Glorious sunshine. The station is about 500 meters behind me, and in front of me, it's only about 500 meters to the IceCube laboratory. I'm going there now to see how our detector is doing. These rods and flags are the only parts of the IceCube you can see on the surface. Most of the detector lies 1.5 kilometers beneath my feet.
IceCube is a superb neutrino detector, a gigantic high-tech ice cube. Buried 2.5 kilometers deep in the eternal ice at the South Pole. It's dark down there, and the ice is extremely pure. Light is able to travel through IceCube without much scattering. The eyes of the telescope watch for the tiniest flashes of light. 5,200 photosensors register the weak light of the particle traces, which can travel many hundreds of meters through the ice. When light signals are discovered, the sensors transform them into electrical signals and conduct these along the steel cables to the surface, to the IceCube laboratory. Into the brain of the telescope.
Hello.
The first computer center has already been installed in IceCube. It registers all the data from the ice, filters it roughly, and then sends it to research centers all over the world. Data from each of the more than 5,000 sensors in the ice is gathered here. This is the detector's control center. It receives its power from here. Thousands of meters of cable and cupboards full of computers. Day and night, a small team of scientists monitors the electronics in the IceCube. To keep the detector running, some of the scientists remain on the ice during the winter. Then it is minus 70 degrees Celsius here, and always night. The sun stays below the horizon. Only the moon follows its regular course. This is perfect for viewing the iridescent polar lights, ionizing solar wind that meets the Earth's atmosphere and is diverted to the poles. But now, during summer at the South Pole, when it's winter in Europe, the sun never sets. It circles the pole at a fixed distance to the horizon. The rhythm of day and night is suspended. The day has 24 hours of sunlight, and you can't orientate yourself on the sun's position. It's just a single day that never seems to end. Jacob van Santen's trip to the high-tech detector IceCube in the Antarctic ice ends after 10 solar days. It's like looking for the needle in a gigantic haystack. The scientists continue filtering the countless events in the ice until they come across the decisive light signals.
This is the raw data. We see the whole detector, but not in real time. I've only read out 1 second here.
But that's 1,000 times slower than real time. Can you switch to real time?
Yes. Then the clip lasts 1 second and blinks wildly.
Filtering the data more and more, the researchers arrive at their goal. A 600-meter-long light trail left by a particle so small that it's invisible.
Now we really only see where there was a strong light signal.
Yes, this is the trace passing through. It's a muon-producing Cherenkov radiation which is being picked up by the sensors. You can see that very clearly.
Ernie and Bert are no longer alone. Since discovering them, researchers have been able to identify other cosmic neutrinos. The one with the most energy to date they have named Big Bird.
We're hoping to be able to identify the sources of these high-energy neutrinos as soon as possible. The big question is, how is this cosmic radiation produced? How is it accelerated? What are the cosmic accelerators that must exist? I hope I don't have to spend the rest of my life researching just these questions, but I definitely want answers to them. The sooner, the better.
Downtown Berlin. Location of the Zeiss Planetarium. This is one of Europe's largest planetariums, and the city administration is making it one of the most modern. The news of the extragalactic neutrinos fascinates the director. To show them in the planetarium dome at the reopening would be sensational. Planetarium director Tim Florian Horn is a specialist in visualizing cosmic phenomena. Using the most modern projection techniques, he wants to make the latest developments and discoveries intelligible to his visitors. The Berlin Planetarium is a modern theater of science.
Whenever anything new is discovered, we want to talk about it and show it. We can help people understand neutrinos best if we can show their path through the cosmos. That works very well in the planetarium because our audience gets an idea of the enormous distances in the universe. In real time, of course, they would need months to fly through the solar system, so we have to suspend some natural laws. We fly faster than the speed of light to a place where, in reality, we would be destroyed by radiation. If we ventured beyond our Milky Way, we wouldn't be able to see other galaxies because our eyes aren't capable of collecting light that long to be able to identify them. It's a fine line we're treading here. We want to be scientifically correct, but also intelligible for the audience. So we have to make compromises in scientific accuracy to make it understandable. Basically, we're a translation service for science.
To visualize the newly discovered neutrinos, Horn meets up with the neutrino researcher Christian Spiering and a visual artist in the animation department at the Potsdam-Babelsberg Film Studios. Their aim is to bring a cosmic neutrino to the screen, to make the discovery of an invisible object comprehensible to a wide audience. None of them knows what a neutrino really looks like.
If we want to represent neutrinos, what can we show? How do we conceive of a neutrino? How might it move through the universe?
I just imagine how a neutrino moves, and I imagine something like the trail of a jet plane without seeing the plane itself. I'm really only interested in how it flies its path through some object. Or I simply imagine a neutrino as the Greek letter nu. That's enough for me. Basically, what I see is a formula.
So then I ask myself, where did they come from? How did they move? And where are they headed?
Look, I'm the neutrino. I fly through space.
So subjectively?
Yes, subjectively. Various galaxies approach, I leave them behind, then comes empty space. Then at some point our galaxy, our solar system turns up, and then a blue sphere in the distance. And that's the Earth.
So far, Spiering has only thought of neutrinos as particles without a shape. The visual artist presents him with various ideas.
That's more like an atomic model, not a neutrino. For me, a neutrino is more like a point without a resolved structure, very, very tiny.
Okay, next suggestion. A model that's more luminous and intangible, with the oscillation on the outside.
That looks more like a dance. Some nice elves capering around a green sphere.
With those bands. I see.
Yeah, a strange oscillation.
This one's interesting. It's out of focus. Might be more interesting, huh?
Makes me think of solar eruptions.
Perhaps the problem is that certain images are already familiar. This one probably looks like Star Trek. It wafts around indecisively in space.
All excited.
Yes, a very excited neutrino.
Before, I saw something interesting in the computer preview, a sharply defined sphere, rather like a billiard ball. If those edges could fray out or blur, I think we would be capturing the ghostly particle aspect. But I'd make it smaller. For me, it's just a bit too big in relation to the screen.
No problem.
Yes, like that. Let's try that.
In the Center for Particle Physics in Marseille, the French research team is getting ready to install the first KM3 net detector chain.
These are the eyes of the telescope, and the photomultipliers are very, very sensitive to light. They can catch just one single photon. The human eye actually requires about 7 photons before you can trigger that you've detected something, whereas these are much more sensitive than the human eye. And we need to measure the position where the photon arrives on the detector with a few centimeter precision. But of course, in the bottom of the sea, we have the sea currents, and in fact, everything is slightly moving. And so inside the optical module, we have some very precise compasses which measure the rotation of the sphere and its inclination in all directions.
In the rare event that a neutrino hits the nucleus of an atom in the ice, it creates a muon, which emits light that activates the individual senses on its flight path. From the direction of the flight path, the researchers can reconstruct the position of the neutrino's source.
The amount of light that we detect in the telescope actually depends on the energy of the neutrino. So if a low energy neutrino was to interact, there wouldn't be very much light, whereas when it's a very high energy event, the whole detector will be lit up like a Christmas tree.
KM3 net will be a powerful deep-sea detector, the counterpart of IceCube in the northern hemisphere. Each detector string is 800 meters long and carries 18 sensors the size of basketballs.
So if you were able to walk around on the seabed amongst the forest of detectors, I think it would be quite an impressive sight to see.
The telescope is not rigid. It floats on the water current. So every sensor has to continuously redefine its position. That's the only way the researchers can determine the direction of the neutrinos. Back to the animation studio. From the planetarium, Tim Florian Horn has brought a software program that can simulate the known universe. In these vast spaces, the team tries to create a dead-straight path for the neutrino, from its source to the Earth.
A graphic card or a computer system can't manage to represent these large scales properly. We have to use a trick. We'll interlace the various coordination systems, so basically we'll fly faster than light.
When we're crossing matter, whether it's an asteroid or the Earth, it would be good to try and zoom in on the atomic level. I mean the level where, as a neutrino, I only see an atomic nucleus in front of me, with a few electrons circling it. Because at the end of the day, an atom is an empty system through which the neutrino flies completely unhindered. Basically, the whole of Earth consists of these empty systems, and that's why it's permeable for neutrinos.
The atomic level should show why the neutrino can fly unhindered through walls and whole planets, a flight through the void. In Marseille, the researchers are preparing to transport a detector string. The scientists roll the string with the sensor spheres into a big ball. They have developed a special anchor to secure it on the seabed. The final step in the construction hall is to load the rolled-up string onto the yellow anchor. The first sensor chain is ready for shipping. Together with the anchor, it's loaded and sent off. A research vessel transports it 40 kilometers offshore. Tonight, the first KM3 net string is due to reach the bottom of the Mediterranean at a depth of 3,500 meters. Slowly, at a speed of 12 meters per minute, the anchor and sensors sink onto the seabed. They are accompanied by submersible robots steered by engineers on board the research vessel. 4.5 hours later, the load reaches the bottom. Robotic arms attach cables linking the anchor with the deep-sea infrastructure that transmits energy and information to the coastal station. Then a buoy hoists the frame. The sensor string unwinds vertically from the metal frame like wool from a ball and releases the individual photosensors to their specific final positions. Assembling the first detector string is successful. Many hundreds more will follow. Soon, KM3 net will also be able to identify extragalactic neutrinos. In the Berlin Planetarium, the researcher animation team wants to take a look at its first results, a cosmic premiere screening. Scientists view the universe as a gigantic laboratory for testing the validity of basic laws of physics and to investigate regions in which gravity, density, and temperature are extremely high. There where stars explode or implode and a black hole is created. A cosmic explosion in a gigantic particle accelerator 1 million light-years away. An enormous jet sent out by a gigantic black hole in the heart of an active galaxy. These jets can reach hundreds of thousands of light-years into intergalactic space. They accelerate the cosmic rays, thereby producing neutrinos. A neutrino flies slightly slower than the speed of light. Since it has only a tiny mass and no charge, other particles don't slow it down or deflect it from its flight path. So it can pass through matter without risking a collision. Atoms, of which our bodies are made, consist of more than 99% empty space. Between the nucleus at the center and the even tinier electrons circling it, there's a great deal of space for the neutrino and nothing but an electrical field. But unlike most other particles, the neutrino doesn't register electrical forces. it has to collide directly with a nucleus for it to be stopped. And that occurs very, very rarely. This rare event can only be discovered with the aid of the gigantic detectors. Only by chance, and with the tiny probability estimated by the scientists, does a neutrino collide with an atomic nucleus in the ice cube. It's enabled extragalactic neutrinos to be identified for the first time. The particles dubbed Ernie and Bert are megastars of astrophysics.
In discovering these cosmic neutrinos, we have opened a new window. However, we haven't opened it fully, just a crack. We know there's something there, but we haven't mapped this new landscape yet. If we find more of these particles and trace them to definite sources, it'll be like a mosaic coming together. And then we'll be able to say how these sources really function, how the wildest machines in the cosmos work. If there are highly developed civilizations in the cosmos, perhaps they don't want to be spied on by underdeveloped civilizations like ours. Maybe they decide not to use electromagnetic waves to communicate, but something quite different. For instance, neutrinos. Just imagine, one day we'd see a kind of Morse code from extraterrestrial civilizations in neutrinos.